So our project is essentially about this robust mobile application for pneumonia detection, and it also evaluates CNN performance with noise and distance variability. And the authors are me, John, and my partner Vihan, who isn't here, and our advisor is Dr. Victoria Liu. So here's just like a table of contents of what I'm going to be covering throughout this presentation. So first we have the introduction, like what is pneumonia, pneumonia's impact in the United States, why accurate diagnosis matters, and then our convolutional neural network for pneumonia prediction, and then also the objectives of our research. Afterwards, we'll move on to the methods, then the results, with our CNN model performance, confusion matrix results, and also the impact of screen distance on model prediction accuracy. And finally, um, oh, did someone say something?
No, go ahead.
Oh, okay. And then finally, we have our conclusion and future work. So, introduction. What exactly is pneumonia? Well, pneumonia is this lung inflammation caused by bacterial or viral infection. And essentially, it affects the air sacs, which may fill with fluid or pus. And some of the symptoms of pneumonia include coughing, having a fever, chills, and also difficulty breathing. So, pneumonia's impact on the United States. Roughly 1 million adults are hospitalized annually due to pneumonia. So, clearly, this is a big, significant problem in our country. And there are around 50,000 deaths per year in the United States that result from pneumonia cases. And pneumonia is particularly dangerous for older adults, infants, and also immunocompromised individuals or people who have impaired immune systems. So, why accurate pneumonia diagnosis matters? Well, obviously, pneumonia is both deadly and contagious. So, it's important that patients are aware that they have pneumonia. And specifically, misdiagnosis or delayed diagnosis can often lead to severe complications or, in some cases, even death. So, therefore, early and accurate detection is critical for effective treatment and also reducing the spread of pneumonia to other people. So here are our project objectives. So first, we wanted to build and train a convolutional neural network using TensorFlow to classify different chest X-ray images as either normal or pneumonia. And next, we wanted to enable broader medical applications. So essentially, we wanted to design the model framework to be adaptable for detecting other diseases, like not just pneumonia, such as tuberculosis and also COVID-19 from this image dataset. And also, we want to demonstrate cross-industry potential. Specifically, we wanted to highlight the versatility of CNN-based models for use in other machine learning tasks across different industries and not just the healthcare industry, like the finance industry, the retail, and also social media. And these industries can also be used for different tasks with CNN models like fraud detection, recommendation systems, and also content analysis. So here's just a reference of a pneumonia versus a normal X-ray image. So over here, pneumonia chest X-ray images are often filled with cloudy areas in the lungs, often called infiltrates, and these chest X-ray images may also show fluid-filled air sacs, which is called consolidation. And pneumonia often either affects one or both lungs, which is called lobar or bilateral. And as you can see here, here are some like key visual cues for the CNN model. So first, the presence of localized or diffuse opacities. Second, asymmetry between lungs. And number three, the disruption in normal lung structure visibility. And on the right side, you can see is the normal chest X-ray, which is pretty different from the pneumonia chest X-ray. And as you can see over here, there are clear lung fields with visible rib outlines. And essentially, there are no opacities or fluid accumulation. And furthermore, there's also normal heart and diaphragm borders. So what exactly is a convolutional neural network? Well, a convolutional neural network is this type of deep learning model that is specialized for image recognition. And it's designed to process and analyze visual data, such as X-ray images. And how it works is essentially it extracts key features from input images, such as edges, textures, and patterns through a series of layers, as you can see in this figure. And why exactly is this so powerful? Well, a CNN automatically learns relevant features without having to actually manually input it, and it's also highly effective in medical image classification tests. And furthermore, it reduces the error by identifying subtle visual differences. And the applications of CNN are pretty broad and widespread. It's used in things such as image recognition, medical diagnosis, facial recognition, and also autonomous vehicles. So here are our methods. So first, we created our CNN model creation with TensorFlow, and the library used was TensorFlow. And we used the same model type as the LRP group. And obviously, the purpose was to classify chest X-ray images as either normal or pneumonia. And our model design, as explained previously, uses layers to extract features like edges, textures, and patterns. And our dataset was obtained from Kaggle. There are around 5,863 labeled chest X-ray images with different categories like pneumonia and normal. And the dataset is from a diverse patient data to ensure generalization of the model, like people from all different ages and gender. And as for our model training, the first step was pre-processing, which was actually resizing the images for uniformity and also performing data augmentation to improve robustness and making sure our model has an easier time reading the dataset of images. And the next step was the training part, which was splitting the dataset into training and validation sets. And essentially, we optimized the CNN and actually increased the accuracy using back propagation and also gradient descent. And our next step after creating the CNN model was to convert it for a mobile deployment. And our tools used was primarily converting TensorFlow to Core ML. And this ensures Core ML is actually compatible with iOS devices. And this is also optimized for mobile performance, and it reduces the file size. And finally, we have our actual mobile app implementation, and we used Xcode for this and through Core ML integration. And Core ML framework was used to load and run the model on iOS devices. And on the mobile app, there's actually real-time image classification directly within the mobile app. And here are our results. So here's like the same training versus validation accuracy as the LRP group. And over here is the accuracy over epochs. And this graph essentially tracks how well the model is learning over time. So first, we have the training accuracy, which is how well the model fits the training data. And the validation accuracy is how well the model generalized to unseen data, like images that they've never seen before. And our goal was to obtain this high accuracy in both training and validation. And this indicates that our model is actually well trained and that it's not actually overfitting. And here on our graph, the x-axis is the epochs, which is essentially a full cycle where model sees and learns from the training data once. And the y-accuracy has the accuracy percentage. And there's two lines. The blue one is for validation accuracy, and the red one is for training accuracy. So as you guys can see here, the general trend is that as the epochs increases, or the amount of times that the model sees the datasets, the accuracy of the model increases. And our eventual outcome was that our training accuracy was around 97%, and our validation accuracy was around 95%. So here is actually a snapshot of our pneumonia detection mobile app. So how exactly does our app work? Well, essentially, users can upload chest X-ray images through the app or use our camera feature. And sadly, the camera feature isn't depicted here, but nevertheless, our AI model still analyzes the image and provides a pneumonia diagnosis. And the model uses our trained convolutional neural network for the image classification. And here are some user interface and features. So our app has a pretty simple design that enables users to upload images easily. And it also provides a clear result of positive or negative for pneumonia. And this is something that we want to implement in the future, but we want to have an option for users to save their results for future reference so that they can reference in the future if they ever want that, or also send their results to a healthcare provider. And here is our confusion matrix, which is also the same as the LRP group. But first, what exactly is a confusion matrix? Well, a confusion matrix is this tool used to evaluate the performance of a classification model. And over here, we only have our 2x2 matrix that compares predicted labels to actual labels because our CNN model is only with two classes, pneumonia or normal. And this confusion matrix helps us understand how well the model is performing, including where it's making errors. So over here, you can see there's the true positive, false negative, and true negative. And as you can see here, our model did a pretty good job of predicting most of the true cases. And specifically over here, the accuracy was around 95.39%, which is how well we did overall. The precision score was around 87.25%, which is when the model predicted positive, how often was it right? And the recall score or the sensitivity score was around 97.16%, which is out of all the real positives, how many did it actually catch? And the F1 score was around 91.94%, which is the balance between the precision and recall score. And finally, the specificity, which is the true negative rate, is around 94.74%. And here are the formulas that we use to calculate it. So now we're going to analyze the impact of screen distance on our model prediction accuracy. So the objective was to evaluate how varying distances, like 10 centimeters to 50 centimeters from the laptop screen, actually affects the pneumonia detection accuracy of the mobile app. So the method was an X-ray image was displayed on the laptop, and then the mobile app was essentially used to predict the pneumonia from different images at different distances, like 10 to 50 centimeters. And here are some of our overall results. 10 to 15 centimeters, the model is actually failing to predict for some cases. And 20 to 40 centimeters, there's a high accuracy in the model detection. And from 45 to 50 centimeters, there is a drop in this accuracy. And specifically, here are our results of the adjusted confidence versus the distance in pneumonia detection. So our objective for this case was essentially to assess how the adjusted confidence of the pneumonia prediction varies with different distances from the laptop screen. And we measured this using adjusted confidence, which is a measure of the model's certainty in its pneumonia prediction, factoring in image quality and also potential distortions due to distance. And as you can see over here in this graph, the general trend is that it has the highest confidence from around 20 to 40 centimeters, and it starts dipping after 40 centimeters. And here is our results for our blur score versus the distance in pneumonia detection. And blur score is essentially this metric used to quantify the blurriness of an image, where a higher blur score indicates more sharpness and also means it is more clear. And as you can see over here, the blur score generally decreases as the distance in centimeters decreases. And this makes sense because as the image distance that the image is taken at increases, the image quality also decreases. And here are our results for the SSIM versus distance and pneumonia detection. SSIM is essentially means the structural similarity index, and it's used to measure the similarity between the X-ray image displayed on the laptop screen and also the original image processed by the mobile app. And as you can see over here, the general trend is that as the distance increases, the SSIM increases too. And finally, we have our PSNR versus distance in pneumonia detection. And PSNR stands for peak signal to noise ratio. And it essentially is this metric used to measure the quality of an image, where higher PSNR values indicate better image quality. And as you can see over here, this is also the general trend. And so for our conclusion, first, the mobile app demonstrated pretty reliable pneumonia detection from X-ray images at different varying distances, as you can see from the previous figures and graphs. And second, the distance from the screen actually significantly impacts the prediction accuracy. And the optimal distance that users should take their image at is around 20 and 40 centimeters. And this will provide clearer images and also a higher accuracy in the pneumonia prediction. And finally, we will continue to use statistical analysis to find the optimal distance guidelines to improve diagnostic performance and ensure users know the required guidelines. And here is our future work. So first, we want to expand to additional diseases. We want to expand the mobile app's capabilities to also detect other diseases, like not just pneumonia, such as tuberculosis and also COVID-19. And this essentially, by implementing disease-specific models, we will enhance the app's diagnostic range. And also, we want to continue to use statistical analysis for optimal distance. And we want to continue conducting this to determine the ideal distance from the screen for the most accurate diagnosis. And then we also want to use this statistical analysis data to refine the app's performance across different user environments and also distances. And also, we want to perform statistical analysis on a larger data set with more images of chest X-ray. And finally, we also want to have future features for enhanced user functionality. So first, we want to add a feature of saving results, which, like I explained before, enables users to actually store their results for future reference. And also, we want to add a feature that allows users to send their results. And essentially, this implements an option to send results directly to a healthcare provider or medical professional. And by doing so, these features can actually be developed to provide this more comprehensive, robust support for patients and healthcare providers. And acknowledgements. So we would like to thank Dr. Liu for giving us the opportunity to conduct this research project and also helping us so much along the way. And we would also like to thank ASDRP for giving us the resources to do so. And here are some of the references for this research. So does anyone have any questions?